Hi, hello, and welcome to the Exam 2 section. As you all know, you have your exam this Thursday, second exam of the course. Woo. Almost halfway there, I think. Like, there's the third exam. I guess you're like 2/3 of the content. And then after Thursday, it will be 2 of the 4 total exams, including the final exam. So, y'all are really in the thick of organic chemistry. So, to be so honest with you, I haven't looked at this little mini exam, which I think will be more helpful to y'all in the sense that, like, we're going to demystify it together and be looking through it and kind of figure out how to approach it. It looks like we have one page of box problems, and then there are 2 pages that are more mechanism focused. One that is a little theoretical with some questions at the bottom. But again, I think that it's not going to take 75 minutes to do that. So I also just pulled the last few mechanism questions from Practice Exam 2B, just because it might be helpful to see approaching some of those challenging like mechanisms together. So without further ado, let's start off with the box problems. Now, anytime we are doing our box problems, the first thing that we are doing is identifying functional groups. And then after we identify functional groups, we are trying to say, hey, are there any reactions that we learned that have these functional groups combining together? So, starting off over here, we have an aldehyde. We know many reactions with aldehydes. And then we have an amine. And specifically, whenever I'm thinking about amines now that we've done lecture 6, I'm thinking about, is this a primary, secondary, or tertiary amine? So can you take a minute and put in the chat, what do you think this is? Is this a primary amine, a secondary amine, or a tertiary amine? Ding dong. For the folks who answered, it is indeed a secondary amine, and it's because we have 2 things attached to our nitrogen. Remember, our amines, primary, secondary, tertiary, is slightly different than how we label alcohols as primary, secondary, and tertiary. So the other key thing that we have here is pH 5. pH 5 is a dead giveaway that we are in the amine, enamine family of reactions. So the question is, which do we form, an amine or an enamine? Well, we know that secondary amines here are going to form an enamine. So the functional group that should be in our product is going to have some sort of like alkene and a nitrogen amine somewhere. So let's do our kind of like fake mechanism disconnection here. So for enamines, what I typically do is I first make the amine version, and then I kind of do the last step of the mechanism. So to form an amine between these 2 components, I'm erasing the carbonyl, instead putting a double bond to a nitrogen over here. So let me just draw that initially. Now, if I just did this, she is crazy. She is a nitrogen that would have 10 bonds. So we know that in the course of the reaction, we are going to be losing a hydrogen on that nitrogen. But still, here we have a nitrogen with 4 bonds to it. So it's locked in with a positive charge. And we don't have any hydrogens that we can easily remove anymore. And so that's why the last step of the enamine formation reaction is we are going to do a deprotonation right here at this alpha position. And then that's going to make a double bond go right here. So for our final answer, we are going to be placing and actually I'll draw out kind of sideways like this. Our double bond there. And then we have our amine with the 2 methyls on it up top. So that is how we form our enamine intermediate. And again, we don't want to be working out full curved air mechanisms for this because it will take far too long. For pages like this, we're going to have many, many reactions on one page. So, any questions on her so far?
Colton, I have one very small question.
Sure.
So I had been writing R, like at the top for the other, you said it's a methyl group.
Mm-hmm.
That's incorrect, right? Like you just leave it knowing on the product that it's like CH3.
Yeah,
Like you
so
only use
like
R
R
to.
is really only a tool for your studying, for like shortening, abbreviating. It could be whatever is on the actual molecules. But here, when we're in exam questions, we are asking you to do the reactions with the actual molecules. So if you did like R and R here, that would get points off because it's not going to be some random R group, which is our kind of stand in for any alkyl group. It's specifically going to be the methyl here because that's what we give you.
Thank you.
Yeah, totally. So yeah, that's just kind of a general note. You should not be putting R in anything on your exam. Okay. Up next, we start off with an alcohol. And then, is this alcohol primary, secondary, or tertiary? Well, for alcohols, we look at the carbon. And this carbon attached to our OH is attached to one other carbon, so it is a primary alcohol. Then we see chromium, which is our big oxidizer. So we just need to know if we are going to oxidize to oxidation level 2, the aldehyde, or if we're going to go all the way to oxidation level 3, a carboxylic acid. So remember, the choice of where we stop at 2 or 3 is going to be our sidekick. So if we have pyridine as our sidekick over here as our solvent, then we just stop at the aldehyde. But if we have water, we go all the way to a carboxylic acid. So that is going to make this carboxylic acid. And she's one of our common carboxylic acids. She's acetic acid. Okay, so now we do our functional group analysis. We are at a carboxylic acid, and then we go on to step 2. Well, step 2 is SOCl2 thionyl chloride. So already I'm thinking about the CAD family of reactions, and then I'm seeing a reagent here with chloride in it. Well, we know that carboxylic acid and thionyl chloride turns it into our acid chloride functional group. So now we are our most reactive CAD. We are an acid chloride. So we could go from here to an ester, to an amide, back to a carboxylic acid. We can go to anything lower in reactivity now. So we are at our acid chloride. And then we have an amine and pyridine. So pyridine is just our solvent here that acts as a very weak base. And here our amine with an acid chloride, that's just going to form an amide. So all we are doing is we're keeping everything the same over here, but it's like we're swapping off our chlorine for nitrogen with a methyl. So we have nitrogen with a CH3. And then we know that some hydrogens are going to get removed in the course of the reaction. If we kept both of those hydrogens on, it would have a positive charge. And so to make it neutral, we just need to remove one of those hydrogens. Because remember, nitrogen is neutral with 3 bonds and 1 lone pair. So that should be our final guy. Interesting. That is not what they put on the answer key, but I'm pretty sure the answer key is wrong. On the answer key, they just put NH2 here. But there's no way that this methyl is going to get like kicked off randomly. So pretty sure that's just an error in the key. Okay. Any questions on this one? This was much more kind of redox and CAD family focused. Okay. So next, this looks insane. This looks like a bug I want to squish.
And I actually did have a question.
Please.
Why would it not be NH2 in the amide product?
So, do you mean just like NH2 normal like this, nothing else? Or do you mean...
No, yeah, actually, yeah. So...
Yeah, so the reason is, like this nitrogen-carbon bond, it's not going to be an easy bond to break. Particularly like in the amide reaction, what happens is this goes and attacks the carbonyl. You have the ClO minus NH2, and then you still have that methyl on there. And then here, you would do like a deprotonation really quick on the hydrogen to make it neutral, and then you would do a lone pair push and kick off the chlorine. And there's just no part of the mechanism that really is involved with this methyl over here. And especially because carbons are hard to remove. That's why it would just stay around.
Yeah, I guess I made a mistake and totally forgot about the methyl and just had two hydrogens attached to the nitrogen.
Totally. And like I feel like that's really easy. Like you saw the functional group transformation. And if you would put some sort of amide, you would get some partial credit. Like that's totally right. The kind of like remembering what everything is attached to is what I call like chemical bookkeeping, of just like making sure all the books line up in terms of like there are no bonus carbons, there are no just deleted carbons. Cool.
Thank you.
Yeah. So now the one that looks like a bug. It's like the little bug's eyes, and then it's down here. Functional groups, that's always where we start. So first off, what functional group is this? Ding dong. We have an acetal. Okay. Then we have a ketone. And then we have NABH4 MaOH, our soft boy, our reducing agent. So, a couple of things. I'm thinking about, okay, who does soft boy react with? Does it react with ketones or acetals? Acetals only do one dang reaction. Acetals only do acetal hydrolysis with H3O+. So, only H3O+ affects this. So we know we're just doing our sodium borohydride reducing agent with our ketone. And that is going to take our molecule from the ketone oxidation level to the alcohol oxidation level. Okay. Now we have H3O+ and H2O. So H3O+, we know that that is going to get rid of our acetal. But we need to remember our strategy for just drawing the product of an acetal hydrolysis. Remember, generally speaking, we have OR going to a carbonyl and two HORs. So our strategy here is we want to find the carbon that's located to both, or bonded to both of these OR groups. We want to cut both of those bonds. And then on the bottom, we put a carbonyl on it. And the ORs that we cut off, we add hydrogens. So over here, I'm finding my carbon that's connected to both OR groups. Then I'm going to cut both of these bonds and replace it instead with a carbonyl. So then the OMEs that I chopped off, I'm going to add an H. And this is just going to be a side product that we don't typically care about in box problems, unless they explicitly say draw out what the side product or byproduct is. Yeah, we don't care. We mostly just care about this top one. So this roughly is our product. But our question says, remember to account for any stereochemistry. And here, do we have any stereochemistry or any stereocenters? Well, this bad boy is attached to a methyl, a long complicated thing, an OH, and an H. And that stereocenter was really created in this step right here. So if we had added the H on a wedge, then this OH would be on a dash. And if we had added the OH on a dash, the OH would be on a wedge. We get both options. So what we're going to do is we are just going to draw one of them. So I'm going to draw the wedge. Doesn't matter which one you draw. And we're going to do a plus minus here to show that we have this molecule, this stereocenter, plus its enantiomer. The only thing to watch out with this notation is it specifically refers to enantiomers. And so it's something that you can't use if there's another stereocenter on the compound that is not also affected. But that's a pretty rare thing to come up. Now, did anyone else get a different product for this? Because it's not in the answer key, but I think there's one other product that would be valid if you would put it. So our final molecule we have an alcohol, and we have an aldehyde, and we are still in acid catalyst. And so the thing that I'm thinking that could happen if we have an aldehyde, alcohol, acid catalyst, we could form a hemiacetal. Okay. So it would be a 1, 2, 3, 4, 5 membered ring. And we are going to connect this O over to this carbon that I've labeled 5 here. So we could form 5. We're now this, and I'll number it all. 1, 2, 3, 4, 5. And now this O that was in the carbonyl is now an OH. And on carbon 2, we need to have a methyl. And then anything else we're missing? I think that's everything. And then we would just have to account for stereocenters. So now we have 2 stereocenters. And so we're going to get a mixture of a bunch of different products. So this would be a hemiacetal. And it's one of those things where I think this is where they wanted you to go. Like, that is what is on the answer key. But if you had done one step further and said, actually, this is going to form a hemiacetal, you would probably get credit. Or you would definitely get credit, because that is the right conditions for forming a hemiacetal. If you did not get a hemiacetal and you just got this, do not be stressed. You did totally fine. You would have also gotten full points. So, okay. I know that was a lot, especially with the little intramolecular hemiacetal at the end. Any questions for that?
I have a question, Colton.
Yeah.
So, obviously completely wrong, but the path that I went down for the first part with the NADH4 and MEOH, I had written down it like a hydride addition. Is that totally, that was down
No,
wrong?
that's exactly...
Is that what that is?
No, that's exactly what happened. Here, from a ketone to an alcohol, we added a hydrogen and its electrons. We added a hydride.
Okay. In my product, I just had, I guess it'd be a acetal. So I had OH, and then I had H, and then another like methyl.
Like this?
Yeah. Oh, so the H is always there. We just don't always write it because it's a sound.
Yeah, just that's our skeletal structure. Yeah.
Oh, okay. So it is right. Okay.
Yeah.
Okay. Thank you.
Yeah,
Sorry.
totally. No, you're good. Okay. So now
if you explicitly write the H, do you get points off?
No, you would just need to make sure to like notate that it's a stereocenter somehow. So if you put the OH on a wedge, you do need to put the H on a dash.
Yeah.
Okay. Yeah. Yeah, I promise we are not like actively trying to penalize you when we're grading. I know it feels that way sometimes looking at some of the comments because they are kind of a lot. Yeah, it's almost something that also that I don't feel like we can help ourselves sometimes, because it's like y'all are learning a new language and we are like going through and editing and proofreading of like, oh, they forgot to capitalize. Oh, okay, they didn't have a period. Like there are a bunch of like little kind of like formalisms that we notice just because we've been in it for longer. And so again, don't let that discourage you. Many of you are getting a lot of the like main ideas correct on the reactions, just some of the little details are still in process. Okay, so now these I always feel like are a little bit harder, where they give us molecules at the start and molecules at the end, and we have to figure out how we got there. So again, first thing, functional groups. Over here we have a nitrile, and then over here we have an ester. Ew. Well, nitrile, we really only know one reaction involving her. We know that we can turn a nitrile into a carboxylic acid, and that's about it. So, let's do that. So the reagents that we need for that, we actually didn't change oxidation level because here carbon has 3 bonds to nitrogen. Here carbon has 3 bonds to oxygens. We stayed at oxidation level 3 the whole time. So really all we needed was H3O+. And you can write H3O+, or you can write H3O+ cat with H2O. Either one works. And then we are at carboxylic acid level. And remember, she is our grand central station for CADs. So if we are at a carboxylic acid, we can go to form any other CAD. Okay, well, we need to form an ester. Well, let's look. We know that to do like carboxylic acid to an ester, we need an alcohol and we need acid. That's our Fischer esterification. But the only question here is really what alcohol do we need to add? So to look at that, for all the CAD reactions, remember, it's just kind of cutting off this side group and replacing it. So if we cut off this side group over here, we see, if we add an H on it, that the alcohol should be this 2-propanol here. So this is the alcohol that's going to have the right connectivity of all the carbons and oxygens to add on and form this specific ester product. So all we are going to add for step 2 is our alcohol and an H+ catalyst. And we don't need in step 3. We're done. Then last one here. Ooh, tricky, tricky. We have over here an acetal. And over here, we have an amine. And particularly, it's a tertiary amine. So there are fewer ways that we know to form a tertiary amine than like a primary amine. Well, we only know one reaction for acetals. We can add H3O+. And again, the answer key does H3O+ cat with H2O, but I think just putting H3O+ works as well. And we know that that is going to do an acetal hydrolysis. So we need to have that same fake mechanism that we had down up here, where we find the carbon that's attached to both ORs. So this is kind of our OR. We need to cut those bonds. And then in their place on that carbon, we need to put a carbonyl. Now that carbonyl looks a little funky, and I actually did this on the other one, but I forgot to make a note of it. Remember, this carbon had a hydrogen there the whole time, but now that we see it's a carbonyl and there's a hydrogen on there, it's just our convention that we draw the H for the aldehyde, just to make it look a little bit less naked. And then the other thing that gets kicked off is this diol here. And she is probably our like little side product that we don't care about. So now that we have done our acetal hydrolysis down here, we are at this aldehyde here with 2 carbons. Well, I mean, one thing that feels confusing is we have this whole boxy boy nitrogen, right? Another thing that we can try to look for is where are these 2 carbons in the product? Does it seem likely that we put these 2 carbons here inside a 4-membered ring? It seems less likely to me that we put 2 carbons inside of a 4-membered ring and something else was happening. Mostly just because we would have to do some bonds with this methyl on the end, and we don't really know any ways of making a methyl more reactive right now. So that makes me think that this methyl all the way over here on the end is going to be this methyl. And this carbon was our carbonyl carbon. Do y'all buy that like argument for kind of mapping out how these 2 map onto here? We have no other methyls in the product. We don't know a way of reacting with a methyl. So it's probably just stayed the methyl the whole time. That's kind of our anchor point. And so now we need to think, what's a reaction that goes from an aldehyde to an amine? And this one is another kind of like classic one, but is often quite tricky for students. This is going to be our reductive amination. So, going and seeing like a nitrogen in the product, you might initially think amine, enamine, which that is fine. Amines and enamines are great. But the big thing here is this is oxidation level 2 and this is oxidation level 1. So we have both added a nitrogen and we have gone down oxidation level. And when you have those two factors together, that's the setup for reductive amination here. So what we need for reductive amination, in addition to an aldehyde, is we need an amine, and then we need that really special reducing agent that I think I called Softer Boy in my little section video, NaBH3CN. And this is a more mild form of NaBH4 that will only react with iminiums. And then we also want to have this at pH of about 5. So the only question is, what's our amine? Well, if we know that these two on the left were from our intermediate that came before, we know that these were from our amine that we added in this step. So I'm going to disconnect. I'm going to have nitrogen like this. And we know that nitrogen likes to have 3 bonds, so I'm going to plop a hydrogen on as well to make it neutral. So that is likely the amine that we added to this aldehyde to do our reductive amination. And then we would not need a step 3. So woof, that's kind of a lot. Questions on these last two? And a valid question could be like, how did we even know we were supposed to do this reaction? Or like, I tried this, why would this not work? Or like, truly, like, throw at me any questions.
For me, I was just confused because I didn't know that a step 2 would be all of this. Like I put the amine as a third step.
Gotcha.
Or
So
the reductive amination as a third step, yeah.
wait, so you did like step 2, NaBH3CN pH 5, and then step 3.
Yeah.
Gotcha. So
Yeah.
honestly, I don't think that they would actually count off for that, because NaBH3CN won't react with a straight up like aldehyde. So essentially you just like add it to the beaker and she's just like sitting there. And then once you add in the amine in the next step of yours, then it would start to do the reaction and it would get to the right product. So like they might like count off like half a point, but that should still get full credit. But yeah, reductive amination, the beauty of it is it all happens in one step. So the pH 5 amine and aldehyde forms an imine, or technically an iminium, and then it's reduced all in the same reaction pot. And the reason that we can keep it all in the same reaction pot is because this is Softer Boy. It's so mild, it allows a whole imine reaction to take place. Yeah. Gabrielle. Yeah.
So I was also confused. I took the approach like kind of going backwards, and I was using the web, and like what I knew from the web. So maybe that was my mistake. But I saw the amine, the product, a 3 degree, or and then so I backed that up, knowing that LiH for an ether could make an amide, and then I was going like up the chain from amide to carboxylic acid, or trying to, but then I know there's only 3 steps, so then I felt like I could have gotten there like with 5. That was like my thought process. Like I understood the first like acetal with H3O plus to get acid chloride, but then from there I struggled to get all the way to the end.
So an alternate version that you could have done that would be totally accurate would be step 1, H3O plus, and that's going to get us to our aldehyde here. Step 2, we could have done CrO3 with H2O, got it to a carboxylic acid. Oh, you're totally right. It would need 5 steps. You're totally right. I was like, then you could do reductive amination, but no. Then you after that you would do to an amide, so you would add in the nitrogen. with like pyridine, and then that would form.
Yes.
There you go. Okay. And then 4 and 5, you do lithium aluminum hydride.
Yep.
And then water, where H3O plus work up. And then that would get to the answer. So
yeah, so I just kept following the web and like a lot more steps. I just couldn't, like, how do you make the decision to do it the way you did with the
I mean, for these, again, I think you both have to work from the start and the finish. So like if you can get to, we know we have to do the aldehyde first, and then we have to get to an amine. It's really clocking, 1, we did a reduction, and then 2, we made an amine. And like, if we only have 2 steps to accomplish this, then the only option is reductive amination. Because otherwise, most of your reductions, like lithium hydride, that's 2 steps alone, and that doesn't even make an amine. Like, we would have to do some other third reaction, so it would just be too many reactions. So, like, again, if you are doing this, like, this is a good sign to me. Like, you are thinking through and you're understanding these reactions and how they can be pieced together. And I'm not sure how much partial credit this would get, but this would get some partial credit because it like follows a clear chemical logic.
I'll take it.
Yeah, no. It's just the kind of constraints of the problem here of only doing 3. And I'll give y'all a hint. You will have reductive amination on your test. We love this. Like, it is like a beautiful thing that combines like multiple lectures of material in a like elegant one-step reaction. It would be a great mechanism. It would be a great box problem. Know her inside and out. Like, really, like, she's... I will pay each of you money if it's not on the test. Only the people on this Zoom, not everyone watching. But, okay, any other box problem questions before we move on to the mechanism? Watch Chris like change the exam and remove the reductive amination, and then yes.
Hey Chris, I had a question.
Yeah.
Oh, I'm so sorry because you said Chris, I said Chris. But anyway,
No, I'll go.
with this acetal, right, that we turned into an aldehyde and then we turned into the amine. I guess like could you kind of like draw out once we remove that alcohol? What are we left with that lets us know that this is an aldehyde? Like, I know we're left with an aldehyde technically and the alcohol leaves, but I'm having a little trouble seeing, like, the split with the OR groups, if you get what I'm saying. That
like,
turns into the aldehyde.
So, like, this kind of disconnection, is that what you're talking about?
Yeah, exactly. Like, how that, like, essentially breaks and then becomes the aldehyde.
So, is your question more about, like, the mechanism and curved arrows into that, or is it, like, visually seeing it at the line reaction level?
Visually seeing it.
Gotcha.
Because I'm like, yeah, visually seeing it.
So, here, if this is our central carbon that we know is going to become the carbonyl carbon, when we break this bond, we have to ask what else is this carbon attached to? And it's attached to this methyl. And then secretly, we don't write it out because it's just implied, but we know that carbon is going to be attached to 4 things, so we know there's also a hydrogen on there. So what we need before we do anything else is we need our carbon, that was our central carbon, we need a methyl on one side, and we need a hydrogen on the other side. And then in our fake mechanism here, when we are disconnecting the 2 OR groups, when we do these 2 cuts that I have in purple, then we are just replacing those 2 bonds that we cut off with these ORs with a carbonyl. And that's what gets us to our specific aldehyde. Did that answer your question? I feel like it might not have.
No. That answers my question for sure. So it's like when we have those kind of like OR groups that are facing away from our central carbon, like we're essentially just replacing that whole function with a carbonyl group instead of like worrying about like those 2 sides. You know what I'm saying?
Yes, and everything else that is on the carbon is just straight up along for the ride. Like this could have been like an ethyl and like a propyl or whatever. But remember, our fake mechanism is only cutting those 2. And so we would need to have an ethyl on one side and a propyl on the other, just because they're along for the ride. That's our chemical bookkeeping, just making sure we didn't make or break any bonds that we didn't intend to.
Word, yes, that makes sense. Thank you, Colin.
Yeah, totally. Okay. So, let's look at this. Wow, this is life-affirming. So fun. form another unique camphor derivative. Okay. So, I know I need to read this at some point, but I have a mental block on it right now because I'm seeing this and I'm panicking. So, first thing I do, the grounding technique in our exam, identify the functional groups. Who is she? Ester. Very nice. And then over here in our products, we have a carboxylic acid and we have an alcohol. Ooh, carboxylic acid, alcohol, ester. Those feel related because we know that if we had a carboxylic acid, alcohol, and H+, it could form an ester. Well, isn't this also what we get when we break up an ester? If we break open an ester, we should get a carboxylic acid and an alcohol. So, this reaction seems to me to be ester hydrolysis. And remember, we could do this two ways, potentially. We could do it in acid, and it just goes there directly, or we could do it in base, and it forms a carboxylate, and then we do a acid workup. So, how does this thing become this thing? Well, we know that in this reaction, we are going to be breaking this bond. Well, maybe let's try to find an anchor point then. If we know that we are going to break that bond. Well, to me, I feel like these two methyls, that is like a really distinctive part of this molecule, right? We don't have any other spot with two methyls. And I see a spot with two methyls up here. Well, can we trace that and make a 5-membered ring? Because we know this 5-membered ring, it doesn't seem to be at all connected to our ester reaction. Our ester reaction is just going to break this open, basically. So, well, we have 1, 2, 3, 4, 5. That's our 5-membered ring. So, we know that this alcohol, this oxygen that's over here, is going to be this oxygen in the alcohol, because that is what's also attached to a carbon that has a methyl. And then we know that this carbon of the carbonyl is probably going to be this carbon of the carbonyl. So now, I don't like it, but I at least feel like, okay, I mapped some things onto each other. I can see where this is going. And then we should always read the paragraph. A lot of times it will be nothing sauce, but sometimes it has something important. Mechanistic studies of this transformation show that an unexpected intramolecular and irreversible deprotonation step occurs. Unexpected. So we know that this is going to be different from our memorized class reaction for ester hydrolysis. And then we need to identify this reaction as either reversible or irreversible. Okay. So, let's see. We start off with our reaction in ester hydrolysis. If we start off with a base, we know that we are going to have a high energy nucleophile. We have OH minus present, and she is just going to go and attack. So then we get to this intermediate. And now we have our OH on there, and we have our other O. Both of them, if we kick this off or we kick this off, they form an O minus as a leaving group. Either an O minus with an H or an O minus with the rest of the R group. And so sometimes, it is going to go and push down, kick off this alcohol. That's just going to take us back to where we were. It's going to take us back to the start. So sometimes that will happen. Other times, this is going to push down, and we are going to instead kick off our OR group. So far, we have not done a deprotonation at all. And we know we are on the lookout for a deprotonation step that's unexpected, intramolecular, and irreversible. Well, at this point in our normal ester hydrolysis reaction, normally what would happen is another OH molecule would come out from the side, would deprotonate this carboxylic acid because it is an acid, and we are still in basic conditions, right? Normally that is what would happen. But again, they said it has to be intramolecular within the same molecule. So what do we have within this molecule that could deprotonate that H? Well, we have this O-. And again, normally doing an intramolecular deprotonation, no, bad. Especially if you're trying to do like a proton transfer, those are typically not intramolecular. Those are two separate intermolecular. But here, because we got a hint in the instruction question, we know that there has to be a step that is going to be intramolecular deprotonation. And then apparently, this is irreversible. So all these steps so far have been reversible. And now we have an irreversible step that forms this. Boop. O minus OH. Now, let's think about why this step would be irreversible. Well, this is an acid-base step, right? So we have pKa's of all this junk. So what is our acid in the starting material? Well, the pK of our acid here is the carboxylic acid, which is around 5. The pK of our product is an alcohol, which is about 15 or 16. I forgot the exact value that they give y'all. So if I use my KQ equals 10 to the pK of the product minus the reactant, this has a KQ of 10 to the 11. So, oh boy, yeah, no, that is irreversible. It is so heavily product favored. And it's because this is a much weaker acid than this one is. Now, why could this be intramolecular? Well, I think it's because it's on this ring already. It's already in the same vicinity. It had just been kicked off, and so it is like at the scene of the crime. And so, because it is so close, because we have another ring that positionally is holding it in a close position to the carboxylic acid, then I think that that's what makes this irreversible. So we are so close here to our product, the only thing that we need to do to finish it off is the second step, the acid workup. So we are going to have a lone pair on this carboxylate, go and grab an H from H3O+. And then we are done. So now it says, in no more than 3 sentences, explain how the thermodynamics of the reaction would be different if it underwent an intermolecular deprotonation rather than intramolecular deprotonation. So we've done this already. We've done this calculation of it being to the negative, or 10 to the 11th, the irreversible. Well, let's do a kind of versus. If we had this molecule and we did the kind of expected deprotonation, we would have this, we would have an OH minus in solution, deprotonate, and then we would get to our O minus, and then we would create water. Well, now let's do our pKa analysis here. Well, here our pKa was again 5. And then over here, our pK of water is 14. So here, the KQ is 10 to the pK of the product acid, 14, minus the reactant acid, 5. So that's 10 to the 9th. So it's still pretty forward, but it is less so than this 10 to the 11th. And I think that that means that it's going to be a reversible reaction, but it's going to be a reversible reaction where the reverse arrow is very, very, very teeny. So it is going to heavily favor going forward to the product. But it's not going to be as impenetrable as the change in pK of 11. And honestly, I feel like this is a very kind of tight argument to make. Like 10 to the 11th versus 10 to the ninth feels like a very small difference. And so, like, if that is not something that you personally picked up on, it's not something that I probably would have personally picked up on when I was in intro organic chemistry. Like, that kind of distinction here of, like, 10 to the 11th as being more irreversible than this. This one's being slightly more reversible. Yeah. So, it's not my favorite question. I'll be totally honest with you. And then question, are you estimating the KQPK based on the functional group's presence? This always feels hand-wavy. So yes, I am estimating it based on the functional groups. And this was the, like, we give you a table, but way back in section whatever, I'm like, I just have these on lock. Like, at any moment, anytime I see an alcohol, I think 16. Anytime I see water, 14. Anytime I see a carboxylic acid, 5. And so these are going to be kind of your benchmark values. And then the pKa, like, on the handout sheet, that has more values, but, like, this is kind of the starting point for all of it. Yeah. Okay. Then last one. One of the carbons in the final product above is marked with an asterisk. Asterisk. What's the oxidation level of that carbon? Oh, okay. So this one. Well, how many bonds does this carbon have to electronegative things? Well, that's a bond to carbon, that's a bond to carbon, that's a bond to carbon, that's a bond to hydrogen. She's boring. She's at the alkane level. Bloop. Cool, I think that's it. Questions on her?
For this problem, this is kind of a silly question, but
No.
in your first step, when you pushed the electrons down and formed the carbonyl, and then you pushed off the oxygen rather than the OH, how did you know how to do that? Because when I first started working through this, like, I totally missed that step, and I don't know if I would have been able to pick that up like an exam.
Totally. So there are a couple levels to it. So one level is, we know the general form of the CAD, like acyl transfer reactions, is you have some sort of carbonyl with a leaving group, nucleophile goes and attacks, you get to your tetrahedral intermediate, and then you kick off the leaving group. Like, that's kind of the essential setup for a CAD reaction. But more specifically, for this reaction from class, the ester to carboxylic acid, in that reaction, after the nucleophile goes and attacks, you kick off the OR group. Like this. And so part of it is, like, the pattern matching of just, like, in the class reaction, it's what you did as the second step. But the other thing that we can think of is, like, okay, we know that this O- is going to be our thing reforming the carbonyl. So what are our options for what we could kick off? Can we kick off a carbon? No, we haven't really seen any reaction do that. And it's because carbons are terrible leaving groups. So our only options really are OH and this OR over here. And both of them are going to be pretty comparable in terms of leaving group abilities. Like, if we kick off OH, it's OH minus. If we kick off this OR, it's OR minus. And both of them are oxygens with a negative charge. They have similar pKa's. So, like, there's not going to be a huge difference. The only thing is, if we go down and push off this OH, we're essentially just undoing our first step where the OH attacked. So, like, it will do this and kick off the OH, and then it'll go back here sometimes because it's reversible. And then another OH will attack, and it'll be back here. And then it might even go back one more time to this ester and kick off the OH yet again. But then sometimes it's going to do a lone pair push down and kick off this OR group. So, like, I think it's kind of playing through, once we're at our tetrahedral intermediate, what are the things that we can kick off? Does that make more sense? Work. Yeah, then it.
Hey, Goldstar, I have another question.
Yeah.
So, do we just know that, like, for example, when I first looked at the starting material in the product, I thought that this oxygen to the right of the carbonyl on the ester to start off with was going to end up being like the oxygen for that, like, alcohol on the right of the carbonyl of the products for the carboxylic acid. And do we just know that it's not that since it's likely ester hydrolysis, so it's going to break open?
So, yes, and also we know that for the CADs, what is the bond we always break on the CAD? It's between the carbonyl carbon and the heteroatom. So if this was an acid chloride, we'd break this bond. If this was a nitrogen and an amide, we'd break that bond. So in an ester, we know we break that bond. So this bond to the side of the carbonyl that's not a carbon, that is the bond that is always broken in the CAD reactions for the most part. So I think that's kind of the pattern.
Thanks, Colton.
Yeah. Cool. And then Fallon had a question. So why wouldn't we deprotonate the negative OH and then proton transfer and lone pair push? So, why wouldn't we deprotonate this to a negative and then after that make this OH and this plus O like this?
I protonated the O minus that you had initially first, and then I proton transferred, and then I did a lone pair push from the O on the bottom right hand corner.
And you had protonated and made this positive, right? To make it a better leaving group?
I had the leaving group as the top oxygen, where you have a negative right now. So I protonated that first and then proton transfer to make it a leaving group. And then lone pair pushed it off from using the lone pairs from the oxygen on the bottom right.
Oh.
Yeah. Yeah.
So. Huh. So, a few things. One, you wouldn't lone pair push from this one. Typically, you could do something like that in an acetal reaction because we form a temporary carbonyl that's attacked again. But here, in the ester hydrolysis, if you're pushing down from this carbonyl, that would make a carbonyl that's forced to have a positive charge because it has another bond to a carbon on it. So it's just not going to be our best lone pair pusher. Our best lone pair pusher for all the CAD reactions is typically going to be either an O minus or an OH. And I think that maybe the bigger thing, though, is the protonation states. So we are in strong base with OH minus. We are never going to make OH2 plus. Because the pKa of this thing is -3, and this is a strong base. And so you're just, it would be like having, I don't know the words. Yeah, when you were in basic conditions, you're almost never going to have a positive charge on an oxygen. Just because we know positive charges on oxygens make the hydrogens on it super acidic, and that just wouldn't happen in base because we're in a strong base. So I think that that's kind of the bigger thing. And then for how to know to do that or not to do that, I think it's more so clocking which reaction it is. Because it seems like what you were doing with the proton transfer and everything seems like the mechanism for the acetal reaction. And if we were starting from an aldehyde or from a carboxylic or an acetal and doing either forward or reverse acetal reaction, you'd be right on the money for what we're doing. But remember, the acetal reaction is always at oxidation level 2, and this is oxidation level 3. And so because they are at different oxidation levels, just react differently. And so I think that it's not clocking correctly what reaction it is. You got thinking in the acetal arrows with oxidation level 2 when we need to be in CAD land with oxidation level 3. I think that's kind of the biggest piece of advice there.
Oh, gotcha. That's really helpful for thinking about it.
Yeah, totally. And then for just kind of where to start, again, I think it's functional groups. Like that is the biggest thing to me. Functional groups, and then when you are studying your reactions, you should be thinking about them in terms of functional group transformations. Like for all the CAD reactions, it's like, okay, I have an ester. What all can I turn it into? I can turn it into a carboxylic acid. I could go down a reactivity and turn it into an amide. I could do double addition and turn it into an alcohol and add some R groups. I could like do a reduction. Like this is the kind of like brainstorming and like our tagging of all of these molecules and reactions. The tags are, instead of using colors, they are functional group labels. And so that I think is part of the studying of like, oh, okay, I need for these functional groups to mean something for me in terms of the reactions that we've been learning. Like I'm sure all of you are doing something to study reactions of like a formula sheet or reaction webs or something like that. And I would just say when you are doing that sheet, make sure functional group names are a big part of that for like how you're like clocking those transformations. Maybe while I'm at it for just general study things, I don't love this. This is too complicated to me. Like, I think it's good in theory, but it's not how I would study. What I would study, and it's just a variant of it, it's the exact same idea, is I would put out a single small functional group, like maybe I'll do an alcohol, primary alcohol, and I would just say, what are all the reactions I could make starting with this? And so, like, I could do an alcohol with CrO3 and pyridine and then turn that into an aldehyde. Or I could do it with CrO3 and H2O and turn that into a carboxylic acid. Or I could put a carboxylic acid and H plus and make that into an ester. And then like you can keep on going. You can be like, okay, how do I make this? I could make this from the reduction of a carboxylic acid with lithium aluminum hydride, and so on and so forth. But I would do them as separate like little bubbles. And then I would go on to be like, okay, now let me do my carboxylic acid one in the middle. What are all the reactions I can do with a carboxylic acid? What are all the ways I can form it? And that to me feels like a much more manageable bite-sized chunks. Rather than let me make one super map that's really complicated. And then also these are easier to study in the sense of like once you figure out how many reactions make it, how many reactions start with it, you can just then on a separate piece of paper draw the correct number of arrows and then test yourself and be like, okay, can I list all the ones? Just to see if you can get them in your head quickly. So that's just a study note, study tip, strategy, all the things. Last question on the mini exam. Predict the organic major product and provide a complete curved arrow mechanism for the following reaction. Account for stereochemistry. Is it reversible or irreversible? Okay, folks. I am seeing a pH 5 here. I know that we are in amine land. And lo and behold, when we look at our functional groups, we have an aldehyde and we have a primary amine. So if we have a primary amine, are we making an imine or an enamine?
One, two, three.
Amine.
Ah! Ding dong! Wow. I love that there's so I think the other Zoomers have clocked it. But I love that there's like a study group that are like meeting in person and watching section. That's so sweet. You all are correct. Amine. And again, we are in the soup of functional groups with nitrogen names of amines, enamines, amines, hemiaminals, amides. But, okay. So, like, this is really just, like, cranking out an amine mechanism. So, maybe I'll say, like, what should you have memorized for the amine mechanism as your kind of guide? Like, just kind of, like, on lock. I'd be like, first step, nitrogen nucleophile attacks carbonyl electrophile. The second and third step you can do in different orders. For me personally, second step I do proton transfer to the neutral hemiaminal. Then you do a protonation to get your water leaving group. Then you do a nitrogen lone pair push off the water. And the last step, you do a deprotonation. Like, when you think of the imine reaction, this should come to mind as your guide in your head of the steps. And also, like, when you were studying the reactions for all of these, think about, can I list out in, like, little bullet points for myself, what should I be doing with my curved arrows? Because once you have your little list and you know the kind of game plan, we can go in here and, like, knock it out no problem. So first step, the amine nucleophile attacks. This is going to make a ring. So I count 1, 2, 3, 4, 5, 6. We're making a 6-membered ring, and one of them is nitrogen. So I'm just going to put that in there. 6-membered ring, one of them is nitrogen. I number 1, 2, 3, 4, 5, 6. And then I need to do my chemical bookkeeping, because I know if I just do it at that, I have lost money. And by money, I mean points on the exam. So the nitrogen, I know, has 2 hydrogens on it. And so nitrogen now has 4 bonds. She's going to be positively charged. And then 2, 3, 4, 5 are all boring. 6, we need to have an O- on it. And we need to have a hydrogen. Okay. Now, it says to account for stereochemistry. Did we make a stereocenter when we did that? We did. 1, 2, 3, 4 different things. So what I'm going to do is I'm just going to choose one of the bonds, make it on a wedge, and then I'll make the other one on a dash. And we know that we get both versions of this, so I'll put plus minus here to say, hey, we make both of these. Now, this is the step where Serenia in lecture and me in section, we did it in a slightly different order, but it doesn't matter. Like at this step, you could first do a protonation of this O, and then make it OH that's neutral, and then do a proton transfer. And when you do the proton transfer, you'd remove a hydrogen over here, you'd add one here. That's totally fine. The way I like doing it is I like doing the proton transfer immediately. So that takes us to NH, and this takes it to OH. And the reason I like doing it this way is because it makes your neutral molecule, the hemiaminal. And I asked like Serenia and Chris, and they said, yeah, both work. And then after that, we do a protonation here, and then we have our water leaving group. So the order that you do does not matter for these. They're both showing the same thing. So I will do my proton transfer. And remember, I don't have to actually draw out that hydrogen, so I'm not, because organic chemists are what? Lazy. Then I do my protonation. And then little things like remembering the plus on this. Okay. So now, what we have done is we have made our OH into a great leaving group. We have packed her bags. We've said, this apartment isn't big enough for the 4 of us. And so the nitrogen, the one with the best lone pair here, is going to push down and say, water, we've had enough. Get out. No water. I don't know where I'm going with that, but that's good. It just turned off the water. Okay. Then we now have this, where we have formed our amine, but we still have the hydrogen on it, so it's positively charged, and so we do our step 5, our deprotonation. So we need something in the solution, probably just a water, is going to just come in, do a final deprotonation. And that will take us to our product over here, which will be this bad boy. So now the question is this reaction overall reversible or irreversible? Well, all of these like proton transfers and things, we know those are totally reversible. Here, we kicked off water, but hypothetically, water could just come back and attack right here. And also just largely, we learned the imine and enamine reactions as reversible. Like we know the imine hydrolysis reaction. If we add enough H3O+, it will go in reverse. So we know that this is a reversible transformation. It's less something to really reason through and more something that's just like a fact that we know about this reaction. So, I think that is it. Questions on this one?
Oh, fine. Hey, Colin,
Yeah.
can I ask another question?
Sure.
For the step where we form the stereo center, do we have to, can we only mark the plus minus on that step? And do we have to show both the wedge and the dash on that step as well?
Thank you so much. I should have put it at all of them. That's a really great catch. Every time we have the stereocenter, if the mechanism wants us to track our stereochemistry, we do have to mark it every time. So, yes, we do need the plus minus on each of them. Thank you for catching that. And then your other question was about putting it on the wedge versus the dash. Is that it?
Yeah, well, it was more so like, for example, since the hydrogens are implied, like, would we have to show both the wedge and the dash on that?
No, not at all. I just did that as courtesy for y'all because y'all are the baby duckling chemists. So I think it's sometimes helpful to write it out. And honestly, if you want to treat the grader as a baby duckling chemist and draw it out explicitly for us, it just shows that you know what's going on. If you don't draw it, we assume you know what's going on unless you do something that makes it clear that you don't know what is going on. So, yeah. Work. Okay, well, with our last little bit of time, I'd like to do one of the mechanisms from practice exam 2B, probably. And to be so honest, I haven't looked much at the practice exams. I just was like, that looks kind of hard. Maybe we should do it. So, does anyone have a preference between maybe question 5 or question 6, which to do? Or also if there's a better question from practice exam A that you think would be good to go over as a group. I'm open ears.
Could we go over practice exam A?
The whole thing?
No, wait. I'm trying to pick up the question in particular. The mechanism, I think it was the first, wait, let me open it up again. I should have actually had it fully set up. The
question 4, maybe?
Yes.
Yeah.
Question.
Yeah, we gave that as a question one summer. Yeah, sure. Let's do it. I think that one's a good one just because it looks really scary. I love doing the scary problems. Sorry, that's really unrelatable. Oh, God. Okay. Like this would have made me like scream a little bit or cry when I was in intro orgo. But now I'm like, ooh, we get to form like a double ring. Ooh, fancy. Okay. Again, our grounding techniques after we have our involuntary reaction. Our voluntary reaction that we do is we identify functional groups. So this looks really wild and wacky, but this is OR attached to a single carbon. That's an acetal. Well, over here, OR, that's an acetal. Are they the same acetal? No. Because this OR was this, and now that is just fully not there in the product. So I think that she's gone girled. Like, I think that she, like, hopped on a train and skipped town, and I think that this is, like, something that was also kicked off because I don't think that she's there in the product. The other thing that we have here is an aldehyde. Interesting. Okay. And then, now that we've labeled all this, we look at our reagent. Our reagent's NABH4-MeOH. Does this react with an acetal? No. The only thing that reacts with an acetal is H3O+. So, we know that this is going to react with our aldehyde. Okay, that's where we start. So, we do NABH4. And we know that this is going to be a reduction of our aldehyde. So we have our hydride that's going to go and be added to the base and make O-. Did I add a carbon? I might have added a carbon. Okay. Thank goodness we can ignore stereochemistry on this, otherwise it would be rough. So, we've added our hydrogen on here, we kept everything else the same. And then we know the second step of the hydro addition is we just protonate it with our methanol. And honestly, these hydrogens we don't need to write out. We can apply them. So I'm just going to draw it. HO, bum, 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 bum. Work. Okay, so that's step one. And then step two, I'm going to do in like a lighter blue. Maybe I'll also just label this as like hydride addition to aldehyde. And this is the interesting thing. So what we would expect is acetal hydrolysis, right? We would expect to go cut, put on a carbonyl, and get something like, if we did cut, we would have our alcohol in the end there. This was the OR at the bottom. We put on a carbonyl, and then we had HOET up top. So we would expect this thing where we have kind of some alcohols on the end, and we have a carbonyl. But what we see is, because we've kicked this off, we know we have to do some of that reaction. We know we need to at least do enough of this acetal hydrolysis reaction that we kick off HOET. But then we are going to be forming a different acetal. So if we don't form the acetal with these two alcohols, well, our only other real option is to use these two alcohols and do like an intramolecular acetal. So kind of let's keep that in mind of doing our like acetal hydrolysis. And then we're going to have a third color, which is going to be our new acetal formation. So I'm going to just list out the steps of acetal hydrolysis to help me. So step one, we would protonate one of our ORs. Then step two, we would do a lone pair push off the HOR. And then step three, we would get to a version that had like a protonated kind of carbonyl, and we would need like water to attack. So like that's kind of like the first few steps, and I could like list out all of them because again, when we're studying our kind of quintessential mechanisms, we want to have the game plan in mind for each of them. So let's start. So I know I'm going to be kicking off this thing, so let's protonate that to get that ready to leave. So I'm going to have this go and grab from H3O plus. Boop. We've done our protonate one of our ORs. And then our second step is we do a lone pair push from the other oxygen. So this kicks off our HOET. And then what we have is this kind of temporary carbonyl, where we have something in the ring attached to the top of our carbonyl oxygen. Well, now maybe let's think about our new acetal formation, because this also could be like halfway through the new acetal formation, and we have like something like step 4, an alcohol nucleophile attacks carbonyl electrophile, and then step 5, a deprotonation. Those are steps 4 and 5 of the forward acetal reaction. So if I think about that, let's try to have this alcohol come over and attack. So when we do that, we are going to be creating a ring, and that ring is 1, 2, 3, 4, 5, 6. Ooh, a 6-membered ring. That's what we want. So we have our bottom ring, where now this is a single bond, which is what we want. And then also at this position, we are making another ring. So another 6-membered ring. So we'd have 1, and let me draw it kind of like the product. So 1, 2, 3, 4, 5, this. But the only issue is like this OH. We know that there's still an H on here. So our last step is going to be to deprotonate. And that's going to get us to our product. So it's kind of tricky where like the way we've made this harder is we've combined 3 reactions and we only did kind of half of 2 of them, right? Like we did the first 2 steps of an acetal hydrolysis where we protonated one of our ORs and kicked it off. And then instead of doing a full acetal hydrolysis, normally in acetal hydrolysis, this is where water would come in and attack, and then we'd work on getting the other OR group off. But now we started to do a new acetal formation. And the reason we know that that happened is because we have an acetal in the product, and it's a different acetal from this first one. So this goes and does an intramolecular attack, and then we just have a deprotonation. Work. So I know that's a lot. I know that's kind of tricky. But any questions on this mechanism? I definitely think this is
super minor question, but I just want to make sure my terminology is correct. In step 1, with the NADH4, that's a nucleophilic attack, right? At that.
Yeah, the hydride is the nucleophile there.
Okay.
Mm-hmm.
Thank you.
Yeah. And then raised hand group.
Hi, Colton. I have a question. Also, this was similar to the one in the PSAT, but I'm wondering why we low pair push off HOR, because also in the PSAT I did like an OR negative, which I thought from the chart in class that was a good leaving group, so I didn't do HOR.
So it just depends on what conditions that you're in. Here, when we are doing all of this junk, we are in acid. And in acid, you will never have a negative charge on something as a leaving group. In acid, you always are going to protonate your intermediates to have a positive charge and then kick it off. Because think about, like, if you were kicking off OH minus, yes, this might be a good leaving group in basic conditions, but that's going to be super reactive when we have H3O plus around. And so, based on whether or not we are in acidic or basic conditions, it also changes what we would expect to be a leaving group. So one thing that you can think about is, like, you're not going to kick off a strong base in acid. Another thing that you can think about is, like, what are the natural protonation states that could happen in acidic conditions? And that would be having things neutral or positive. Like, you'll notice that once we got into H3O plus at this step, we no longer had a negative charge for the rest of the thing. We only did positive charges. And you'll notice that when you're in base, like this reaction, we had no positive charges. We only had negative charges until our last step when we were in acid. So I think it's more of a protonation states thing to clock of if we are in acid or base, what can be our leaving groups and what protonation states are accessible. But did that kind of answer your question, or did that only make it worse?
Yes, thank you.
Work. And then someone had their hand raised. Was it Zara?
I had my hand raised, but it was about like a totally different thing, so I just wanted to let you still talk about that.
Okay. Yeah, you can go ahead and ask your question.
Okay, it's like totally switching gears, but it's on problem set 6, or not the problem set, it's the practice problems.
In that case, I'm going to pause because I do,
Okay, yeah.
if it's a question about like what we did today or kind of general exam thing, I'll take it now. But otherwise, I'm going to end the section video and then I'll start my office hours in like a few more minutes after that. And then that we can go over kind of whatever. So,
Sure. Yeah, that's fine.
Cool. Can I do last call for the section review or just general exam things? I don't know. This is the scariest exam to me. It's the first reactions, and reactions is like, okay, we're really in organic chemistry. I've done very bad on these exams before. Like my first exam of OChem 2, I got a 39, and 10 points were given to us. So I really got a 29. I said, wow, I bet I can't be a doctor now. So like those feelings are very normal and are around. And I know I've been doing it for like 10 years, and so now it feels really easy. But like, it's just a learning curve, like learning any kind of language. But y'all can do it. I believe in you. Thank you for coming to section, and now I'm going to take a little break, and then we will do office hours from 7:30 to 9:30. So stick around if you have questions.